Hi everyone. Today I'd like to talk about a joint work with Song on the convergence rate of the vanishing viscosity process for a type of state-constraint Hamilton-Jacobi equations. First, let me introduce the problem in more detail to you. We consider omega to be an open bounded connected domain Rn with C2 boundary, and F is a given function which is continuous and Lipschitz. We first look at the second order state constraint problem where our Hamiltonian is absolute value of the gradient to the P minus F, where P is between 1 and 2. And also we have minus epsilon times the Laplacian term for epsilon greater than 0. We require the left-hand side to be less than or equal to 0 in the interior of our domain, and also greater than or equal to 0 on the closure of our domain. This actually imposes a boundary condition on the solution U epsilon, which will be discussed shortly after this introduction. And it is actually the boundary behavior of U epsilon that makes this problem interesting. And it can be proved that U epsilon is actually C2. As epsilon tends to 0, in the limit, we have the corresponding first order state constraint equation. And the solution can be shown to be continuous up to the boundary. So here, both of the solutions are in a viscosity sense, and we will give the definitions together with well-postness and properties of the solutions in a second. It is well known that U epsilon converges to U locally uniformly from the PDE point of view by Lazari-Lyons, Capuzzo, Dichata, and Lyons, and from the stochastic point of view by Fabry, Gozzi, and Switch. What we are interested in here is its convergence rate. Namely, can we prove the uniform distance of U epsilon minus U is bounded by some constant times epsilon to some power. So here is the outline for my talk today. First, I will introduce the basic properties for our second order and first order state constraint equations. Then I will present our main results together with summary of the proof ideas. In particular, I will talk about how we use doubling variable method to get O square root of epsilon convergence rate. Let's take a look at the second order state constraint problem. We say U epsilon solves the second order state constraint problem if U epsilon is a viscosity subsolution in the interior and a super solution on the closure of the domain. Here, when we say subsolution, we mean if we have a smooth function phi that is touching U epsilon from above, or equivalently, we have U epsilon minus phi attains its max at some point x0. We take our the left-hand side of our second order equation with phi plugging in and evaluate it at the point x0 is less than or equal to 0. And similarly, for super solution, we mean if we have a smooth function phi that's touching U epsilon from below, or equivalently, U epsilon minus phi attains its minimum over the closure of the domain at some point x0, then we take the left-hand side of our second order equation with phi plugging in and evaluate it at the point x0 is greater than or equal to 0. When P is between 1 and 2, equivalently, U epsilon is a unique solution to the second order equation with the blowing up condition on the boundary. Actually, by Lazari-Lyons paper, they proved the well-postness of this second order equation. Namely, there exists a unique solution U epsilon, which is C2, and we know roughly how they blow up near the boundary. So for P strictly between 1 and 2, we know U epsilon near the boundary is roughly some constant times epsilon to the power alpha plus 1 over d to the alpha. So here alpha is a non-negative constant that depends on P, and the function d is a smooth version of the distance function from the boundary. And for the case where P is equal to 2, the blowing up rate is like minus epsilon times natural log of our distance function. So this is the basic properties of our second order equation. In the limit, we have our first order equation. The solution describes the optimal value function of optimal control problem, where the running cost is actually the Lagrange transform of our Hamiltonian. So our Hamiltonian P is between 1 and 2. So here Q is actually greater than or equal to 2. And also we require all the paths that starts at X stay inside our domain. And this is where the name state constraint comes from. So we have this requirement. And it can be shown that this solution U is continuous up to the boundary. As we just saw for the second order state constraint equation, the solution blows up near the boundary. But here for the first order equation, the solution is continuous up to the boundary. So we expect to see the boundary layer behavior when we look at the convergence rate of U epsilon to U. Here is the main results, which consists of 3 parts. We will always assume F is continuous to the boundary and Lipschitz, and also we assume F is non-negative with its value equal to 0 on the boundary. The first result says in the interior of the domain, we have O square root of epsilon rate, or more precisely, when P is strictly between 1 and 2, we can bound U epsilon minus U by negative C times square root of epsilon, and the upper bound is some constant C times square root of epsilon plus the term which corresponds to the blowing up behavior of U epsilon near the boundary. And for P is equal to 2, instead of epsilon to the alpha plus 1 over D to the alpha, we have epsilon times the absolute value of natural log of D, which corresponds to U epsilon blowing up near the boundary. And for this, we can consider 2 examples. So if we look at all the compact set K inside our domain, which means the distance function is bounded below by a positive constant. And we can see our convergence rate is O square root of epsilon. And the second example is we can look at the boundary layer O epsilon, which means we look at all the points inside domain that are distance epsilon away from the boundary. So here our distance function is bounded below by epsilon, and still we have our O square root of epsilon convergence rate. So this is our first result. And the second result, we assume F is compactly supported, and we add an additional assumption, which is F is semi-concave in its support. Here, semi-concave roughly means the second derivative of F is bounded. So this case actually includes the functions that are compactly supported and C2. So for this case, in the upper bound, we have epsilon instead of square root of epsilon. So here we have our improved one-sided O epsilon rate. And this result is for P between 1 and 2, strictly between 1 and 2. Okay, and then the third result here is what we assume F is C2, and also its gradient is equal to 0 on the boundary. And in this case, we have improved 1 epsilon, O epsilon to the 1 over P rate. So here you can see this rate is a little bit better than square root of epsilon, but it's a little bit weaker than O epsilon rate. And this result is for P between 1 and 2. And actually, this result is not hard to show. What we did is, for this case, our function can be uniformly approximated by compactly supported C2 functions. So we will take our second result and pass everything to the limit, and this can be done. So the third result is deduced from the second one. And also the lower bounds here for U epsilon minus U is not hard to prove. it can be deduced from a well-known rate for Dirichlet boundary problem together with comparison principle of the second order state constraint equations. So our focus here is to prove the upper bound for the first result and the second one. So here is a summary of the results I just showed. So for the first result, we have O square root of epsilon rate. And there we will use doubling variable method to prove the result. For the second improved one-sided O epsilon rate, because we assume F is semi-concave in its port, we can actually prove our solution U to the first order equation is locally semi-concave. And that will help us improve our upper bound. So the second result is proved by using semi-concavity. And the third one is the improved one-sided O epsilon to the 1 over P rate. As I mentioned, this one is deduced from the second one by uniform approximation. Next, we will look at in detail for the proof of the first result. So we want to prove the O square root of epsilon rate for the most general case where F is only assumed to be 0 on the boundary. In order to do that, we first prove for the case where F is a constant, and then we move to the case where F is compactly supported. And in the end, we can prove the most general case. So if the first two cases are done, the third case is not hard to show, again, by uniform approximating by compactly supported functions, and we can pass it into the limit, so we will get our desired convergence rate for the third case here. So the math focus is the first two cases. So for the first one where F is a constant, we use the optimal control formula for the first order equation U, and also we construct a super solution explicitly to control U epsilon, and we can get our result there. So for the second case where F is compactly supported, we do use doubling variable. And before I give the detailed argument, I want to go over a heuristic argument with doubling variable method. So if we use the classical doubling variable method, we would define an auxiliary function phi of x comma y to be u epsilon of x minus u of y, and we subtract a quadratic term, which is the absolute value of x minus y squared over the constant sigma, where sigma is to be determined. And we assume phi has a max at some point x sigma, y sigma, and we further assume x sigma is attained in the interior of our domain. So here, this assumption, x sigma in the interior, is actually problematic, and we will talk about that in a second. But for now, just let's assume this is true. So if this is true, we can use the definition of phi attaining its maximum at x sigma, y sigma to compare the function value there with any other point. So here I pick another point, which is x sigma comma x sigma. So this is greater than or equal to the function value at this point. And if we rearrange terms, we will be able to control the absolute value of x sigma minus y sigma by constant times sigma. So if we choose sigma small enough, the distance between x sigma and y sigma is small. And then we just use the typical argument in doubling variable, which is we treat our quadratic term as a test function for both u epsilon and u in the second and first order equation. And using the definition of u epsilon being a subsolution and u being a super solution, we can deduce these two inequalities with quadratic terms plugging in and evaluate it at x sigma and y sigma. And then we just subtract the two inequalities. We will get u epsilon minus u is bounded above by some constant times epsilon over sigma. plus some constant c times sigma. And we can choose sigma here. So the best choice we can make is we choose sigma to be square root of epsilon. And you can see here, basically we are done and we get our O square root of epsilon rate. But there is a problem with our assumption for x sigma is attend in the interior. Because as we saw just now, U epsilon is blowing up near the boundary. So phi will never attain its maximum inside the interior. It will always happen on the boundary. So in order to deal with this, instead of the previous definition for phi, we subtract one more term here. So this term is more or less the blowing up rate of U epsilon near the boundary. And we can make the constant C alpha a little bit larger so that we force the max to occur in the interior. And then we can carry out our previous argument. And using test function instead of the quadratic term, we use the quadratic term together with this actual term. But because we involve this actual term, when we do the inequalities, when we're plugging in, and in the end, in the inequality for U epsilon minus U on the right-hand side, instead of the two terms here, we will have more terms. For those terms to vanish, we need to require the distance of x sigma to be about epsilon to the gamma for gamma less than 1. So this is saying if x sigma is attained away from the boundary, then we are good. We can use our doubling variable method and then get the convergence rate. But if x sigma is attained very near the boundary, then we have a problem. So here we use another trick. Suppose our support of f is inside a domain, we call it omega sub kappa, and where it consists of all the points that are distance kappa away from the boundary. So as I drew here, it's a little smaller domain here. And we still define our auxiliary function phi as before. And now we can break into two cases about where this x sigma is attained. If it's attained in the interior of inside omega kappa, then this is a case where its distance is bounded away from the boundary by a positive constant. So this is much stronger than we need. And then we are good. We just carry out the doubling variable method. But if this x sigma is attained inside the annulus part outside our support of f, then we consider something else. So first, inside this annulus part, our f is 0. And from the optimal control formula, we know u is 0 inside the annulus part, as I drew here in yellow. And then we consider a barrier function u epsilon tilde, which is the solution to the second order equation with the blowing up condition on both of the inner and outside boundary here. And this is exactly the second order state constraint problem on the annulus part. And there f is 0, and we can use our result from the first case where f is a constant. So we can control our convergence rate of u epsilon tilde to u in the annulus part. But also in this annulus part, if we look at u epsilon, it also solves the second order equation, but the boundary condition is a little bit different. For the outside boundary, u epsilon is blowing up. But for the inside boundary of the omega kappa here, u epsilon is actually finite. So by the comparison principle of the second order equation, we know u epsilon tilde is larger than u epsilon. So we can control u epsilon minus u by u epsilon tilde minus u. And we just borrow the conclusion from the first case, and we are done with the proof for f compactly supported. So this is the main idea and how we can overcome the difficulty when x sigma is attained in the annulus part. Okay, so here are some open questions for our project. So first one is, we always assume f is equal to 0 on the boundary because we use compactly supported functions to approximate. So one direction in the future may be, can we remove this assumption? And maybe we need to use other methods. And the second one is we don't know the rate we get is optimal. So we can try to find out what's the optimal rate for the convergence. And the third question is, what happens when p is greater than 2? When p is greater than 2, the second order state constraint equation doesn't have a blowing up condition on the boundary. And in fact, the boundary condition is finite. So it's a totally different case. And there, we haven't carried out the computations and project there. So this is a future direction. And I think this is the end of my talk today. Thank you so much for your attention.